information. He's a World Economic Forum Fellow, a Fellow of the American Association for the Advancement of Science, and a Fellow for the American Mathematical Society. His current research is focused on the use of different media to teach and communicate mathematics to diverse audiences. He has written 33 books and over 80 published research articles, has received numerous prizes. We know and love him as the Math Guy on National Public Radio. Please welcome.
Thank you. Good to be here. Brian and I have been planning this for months in how we would dress. You want to put that on me? I can use this.
No, but I need you to use this.
You need that as well? Okay.
I do.
You're recording this, aren't you?
The people in Africa need this.
Yeah, I could shout loudly. But okay, so yeah, Brian and I have been working very hard for months trying to plan how we would start this off. So you'll notice that Brian was wearing a jacket and a tie. I have a jacket and no tie, and after us, everyone else fits right in perfectly for the rest of the day. In fact, I'll probably take my jacket off, and I suspect Brian will too. I spent a lot of time, put a lot of effort over the years into sort of outreach to various audiences, through radio, working with movie directors, that kind of thing. So writing books, articles, magazines, and so forth. And a lot of the time, I spent quite a bit of time thinking about simple little phrases that can catch on, that people can use. They're not always mine. I sort of stole the idea that mathematics is a science of patterns. It's not clear who first used that. It sort of appears going back to the 50s. But I wrote a book called Mathematics, a Science of Patterns on the Scientific American Library series to really try to make that sort of stick as something valuable, to give the right sort of feeling to what's going on. Another one that I came across that I thought was original, but I found somebody else has also used it, was Mathematics Makes the Invisible Visible. And I think it's important to sort of get these little pithy statements that sort of capture important insights into mathematics. And I'm just going to share with you a couple of the ones I've started using a few years ago. One is, calculation is the price we used to have to pay to do math. And by calculation, I don't just mean with numbers, I mean executing algorithmic procedures. Because for almost the entire history of mathematics, unless you could do that yourself, you couldn't get in, you couldn't get accredited, and you couldn't do it. There was no other way except sitting down and grinding it out with paper and pencil or whatever. But since calculators came on the scene in the 60s, and computer algebra systems and things like Wolfram Alpha beginning in the late 80s, all of that's been automated, so it's no longer the case that calculation and execution of procedures is essential, because nobody in the business does it anymore, and you don't need to learn it. What you need to learn is the correct kind of understanding. That's why it's important to do exploding dots, not the classical algorithm, because the exploding dots makes you understand what's going on. So people think you're just giving over to the machines. No, we're learning how to make use of incredibly powerful, ubiquitous, very cheap machines. And that's completely revolutionized the subject, completely revolutionized it. So there was that little thing about calculation is the price we used to have to pay to do mathematics. The other one is, and it's not as simple, it's a simple little image. I try to liken mathematics today to music. To be a mathematician in the era when I learned it in the 60s and 70s, when you had to learn all sorts of stuff, it was like wanting to be a musician and going into an orchestra. I had to learn a lot of instruments. I had to learn the arithmetic instrument, the algebra instrument, the geometry instrument, the trigonometry instrument, the calculus instrument, the probability theory instrument, the linear algebra instrument. You had to learn to play as many instruments in the orchestra as you could, because that was the only way to do it. You had to get down and do it. There were no machines to do it. Once we had everything automated, being a mathematician was not like playing in an orchestra, it was being the conductor of an orchestra. You have this array of stuff it's on your iPhone, it's in the cloud, you have access to all of this stuff. Just as a conductor needs to understand what all of those instruments are capable of, how to get the most out of them, probably plays one of them very well, usually the piano, probably plays a few others moderately well, but they're not world class in any of those. They don't need to be, because they have all of the world class people in front of them. The conductor needs to have the right understanding to coordinate all of that incredible creative power. And that's what it's like to do mathematics today. I'll leave you with one little story about a course I gave. I gave it in Princeton for a while and then a couple of times, and I gave it at Nueva School down the peninsula last January. I'm doing it again this January. I took a group of students, mostly high school, some middle school students, groups of 3 or 4. It was a 3-day course, 2 hours a day for 3 days in a row. Or maybe it was Monday, Wednesday, and Friday. I forget the exact details, but it was 6 hours. The goal at the beginning was that after 6 hours, working in groups, those students were going to reconstruct or reverse engineer the basic package routing algorithm for UPS. Step 1, send a package, track it in detail, and then think to yourself, all of those things that that package did, and it's usually pretty complicated, were for a reason. It turns out that if you're lucky, and you're a little bit lucky if you have no problems, so long as at least 1 or 2 problems arise on the way, you actually have enough data by shipping 1 package to reconstruct the algorithm. Now, okay, I can do it because I know all stuff about linear algebra and simplex. I mean, I've been in the business for a long time. The point is, with me just as a consultant, those groups of kids, after 6 hours, essentially got the algorithm, and they did it by brainstorming and being creative human beings, using the technologies as and when they needed to. And if there's one thing anybody under the age of 25 just takes naturally to, it's using technology. Start with Google and then narrow down from there. It's unbelievably creative, it's a lot of fun, and it's how the professionals do it anyway. So great time to be a teacher, great time to be an educator. Actually, it's a great time to be a teacher if you're coming in. If you've been in the business for a long time, it's got to be one of the scariest things around. But it's really exciting for mathematics. And as I think I actually wrote a commentary on James Tanson's Exploding Dots, because I heard about it and I thought, well, isn't that just what I'm thinking all the time? And boy, it suddenly struck me, that was the brilliance. What he found and what he did was be able to go inside mathematicians' heads and find a way to represent what the professionals do on a whiteboard or a blackboard in a way that can spread it out to everybody. So he's mainlining mathematical thinking into the next generation, and it's brilliant. Delighted to be here as part of this enterprise.